Yang, yeah. Shi Yang, yeah. Now it's your time to share your screen. And Yang was a very amazing person. So I think the most thing I want to say, yeah, Yang has very good English speaking. And the first time you get on the stage on mine, that time I say, okay, where you learn your English? It's in UK now. Now you're teaching in UK. So you're going to talk about the nanoionic in emerging energy storage technology. Okay, yeah, Xiang, stage is yours, please.
Thank you, Alice, very much for the kind introduction. And first of all, I would like to thank iCAN X to provide such a good opportunity for me to showcase my research, but also to provide such a good platform to bring together people from all over the world with different, diverse background to be sharing their opinions and research in experiences. I think this is particularly important at this time, at this difficult time where everything seems to be a little bit crazy, maybe even crazier here in the UK than in China. So the my talk today is a little bit different from the previous two speakers. Uh, their research is quite heavy focused on the device fabrications. But my talk is more looking at the fundamental science in the material setting. So we're looking at how to make materials work better for the merging and emerging energy storage technologies. As you can tell from the name, the technologies are emergent. So there is a bit different distance for the technologies to be able to be commercialized. But we're working very hard. We're looking at the fundamental science that would define the future of these new emerging energy storage technologies. I usually like to start my talk with sharing a little bit news, as battery is a very fast forwarding landscape. So what you can see right here is news from the BBC in 2019. So the figure on the left shows the composition of the electricity generated in the UK. And what we're particularly interested in is the renewables and the nuclear energy because they're clean and they represent the future of human beings. So the news that I would like to share came from last year. I think it's between January and May 2019. During that period of time, or I think ever since that period of time, it is the first time since the Industrial Revolution that Britain has been able to obtain more power from zero carbon sources than the traditionally used fossil fuels. I think that's a very important step forward towards the goal of zero carbonization. Speaking to carbonization, we can imagine a whole lot different pictures for this topic. But one important aspect of carbonization is to provide energy storage technologies that can save energy, that can save green and clean energy for use. So we can use this energy in all kinds of different applications. For instance, powering electrical vehicles, which is a huge topic all over the world at the moment. This is just coming last month that the UK government has taken a very, very important step forward towards net zero emission. They announced that they will stop selling the cars that powered by petrol and diesel by 2030. So this is actually a very significant step that the government is setting up to. The original goal is set to be around 2040, and now the government is pushing forward this deadline to 2030. And besides powering the cars, we're also looking at energy storage at an even bigger scale, where we can use energy storage technologies to save energies that are generated by large scale ways, for instance, hydro energy, for instance, wind and solar energy. And another thing that is probably more, even more close to us is the home use energy. So the smart home energy use is a very, very new concept that just came into the spotlight. So all these aspects can contribute to the decarbonization process. As I said, we need a reliable and green and clean solution to save energy in order to work towards decarbonization. So for this, I think batteries-based technology presents a very, very promising area, a very promising solution for decarbonization. And this is why my research has been focusing on batteries for perhaps I would say the last decade, from lithium, sodium, potassium. So let's have a look at what's happening right now in the lithium-ion battery market. The Faraday Institute here in the UK has recently published a insights, which is called the gold rush of the 21st century. So the gold rush here, I think, meant the raw material resource for making lithium-ion batteries, which typically include cobalt, lithium, and nickel. And they have made the estimation that the demand for these raw materials of making lithium-ion batteries will have a huge increase in the next 10 years to 20 years time, which is not surprising because lithium-ion batteries have dominated the portable electronics market for over 2 decades, and we're looking at powering cars using lithium-ion batteries. But if we look at the Earth's abundance of lithium, which is shown here, actually the Earth's abundance of lithium is quite low, only 0.002%. But interestingly, if we move towards the right-hand side, right here, we found that the Earth's abundance of sodium and the potassium is actually at least 3 magnitudes larger than lithium. So that makes us think, can we use sodium and the potassium to replace lithium and use sodium ion and the potassium ion batteries as the future green and clean battery technology? I think my answer is a firm yes. I expect that there will be an audience tonight from the general public and also audience from other research areas. So I would like to use a couple of slides to, briefly introduce, to explain how sodium and potassium ion batteries work. In principle, sodium and potassium ion batteries work in the same way that lithium ion batteries work, which is called a rocking chair batteries, where the lithium ions, well, in this case, sodium and potassium ions, shuffling around between anode and the cathode to deliver the charge back and forth. As I said in the last slide, cost advantage is the major motivation for us to look at these new technologies. So on the right-hand side, what we can see is a battery performance and cost estimation using widely accepted mode, where we try to estimate the cost of lithium-ion batteries in relative to sodium-ion batteries. There are a couple of things that really strikes as a very promising indication. The first indication is the cathode, because in lithium-ion batteries, we're using materials that contain lithium as cathode materials. So if we can switch, we can replace lithium in the cathode material with sodium, making a sodium-containing cathode material, we can potentially save the cost of making the batteries. And the second indication, which is even more significant than the first indication, is the cost of the current collector. In lithium-ion batteries, the current collectors are aluminum and copper, aluminum for cathode and copper for the anode. Because the cost of copper is at least 3 or 4 times more expensive than aluminum. But we can actually replace copper with aluminum for both cathode and anode as current collectors. So this switch seems to be little, but if we look at the cost, it can significantly reduce the cost just for the current collector. Combining the cathode material and the current collector, we're looking at potentially a 10 to 20% save of the cost. So that's a very, very brief introduction of sodium and potassium ion batteries in terms of, in relative to lithium ion batteries. I know there are people who are working in this area may have the question that because sodium and potassium are quite heavy, to be honest, much heavier than lithium. So the volume, both the volumetric capacity and the specific capacity of lithium is significantly higher than sodium and potassium, which we can see from the right-hand side of the slide. I would like to point out that it is a very common misunderstanding of sodium and the potassium ion batteries, and I often got asked by this question. So I think the confusion here lies in at how detailed you know about what's inside in the battery cells, because we don't really have the metal lithium, metal sodium, and the metal potassium existing in the cell. It's the ions that in the electrolyte carries the charges back and forth. The only bit that we have lithium, sodium, or potassium is the cathode material. So these volumetric and specific capacity are calculated based on using lithium, sodium, and the potassium metals as the anode. So that would give us the misunderstanding that sodium and potassium ion batteries may not be as competitive as lithium. But I think considering the small amounts of metal were used in the cathode material, these disadvantages isn't really that significant. Previous work has used the simulation to estimate the energy density of these 3 types of battery technologies using the 18650 battery as a mode, where we take graphite as the anode and we take the metal cobalt oxide as the cathode. We simply change the metal from lithium to sodium to potassium, and in order to estimate how much actual energy density we can obtain from the 3 types of batteries. The results showed that for a typical 18650 lithium-ion batteries, the energy density is 279 watt-hour per kilogram. And the numbers for sodium and the potassium is 231 and 218. So you can tell that the actual energy density that is delivered or that will be delivered by lithium and by sodium and potassium ion batteries are just slightly lower than lithium ion batteries. And these estimations are based on considering cathode, anode, separator, and electrolyte in the cells. Keep in mind that there's a lot more than just what I said in the cell. We have to consider the packaging. We have to consider other aspects in the cell that take even higher weight out of the actual material. So this difference will be even less significant when we're considering every single part of the batteries. So I personally believe that sodium and potassium ion batteries in the future will have the potential to catch up with lithium ion batteries. And that is also the reason why I have been working on these 2 different types of batteries for the past, I would say 3 to 5 years. But sodium and potassium ion batteries are not all fancy as we think it would. The major challenging to develop these two types of batteries is the size of the ions. We all know that the size of sodium and potassium cations are significantly bigger than sodium. So what that would tell us in terms of battery operation, if the charge carriers has a larger size, the diffusion of the charge in the material, in the crystal structure of the material, would have a much larger resistance. This resistance sometimes causes the the local deformation of the crystal structures. In some cases, it would even deactivate the material, so the material wouldn't show any electrochemical activity to be used for the batteries. So the focus of my work is to develop the material design strategies to overcome the bigger size of the sodium and the potassium ions. What we are particularly interested in for the past 5 years is to design the material at a nanoscale. Specifically speaking, we're trying to introduce disordered structures in the commonly considered ordered structure materials. We have been working on this aspect from two different angles. The first angle is to create local atomic defects. So these defects are in a short range of disorder. We have been applying this strategy in various materials, for instance, carbon materials, sulfides, and oxides. And we also apply this strategy in a relatively longer range, where the defects inside the material are extended to a large area. Eventually, the material changes from crystalline to amorphous structures. So we had some work regarding oxides, where the oxides have the long-range disordered structures, even the amorphous structures. What we aim at is to use this long-range and short-range disorder to create pathways to direct the ions to diffuse inside the crystal structures in a certain diffusion pathways. Therefore, we are able to enhance the ionic diffusion and at the same time increase the surface ion storage in the nanostructured materials. That is the reason why I had this title of my talk today, the nanoionics, which means the ionic diffusion in the nanostructured materials. So due to the time limitation, I won't be able to explain all the work in this slide. I will just use a couple of examples to showcase our design strategy. I would like to start from the carbon materials because it's a very sustainable material. It's low cost and it has the ability to be scaled up. So what we have done is to use the nitrogen doping in the carbon material to create the carbon defects. These defects could not only enhance the diffusivity of potassium ions, but also increase the surface storage of potassium ions. The nitrogen doping usually exists in 3 different types of forms: nitrogen 5, nitrogen 6, and then nitrogen Q. Nitrogen 5 refers to the nitrogen in a 5-member ring, which mimics the environment of pyridine. And the nitrogen 6 refers to the nitrogen, the purple ball here, in the 6-member ring, which mimics the pyro environment. And the nitrogen Q is the orange balls right here, which mimics the graphite environment. What we did experimentally is to use a very simple polymerization method to obtain the polypyrrole at first, and we carbonized the polymer at a different high temperature in order to control the degree of carbonization of the material. The degree of the carbonization also determines the types of the nitrogen doping, therefore the level of the carbon defects. We were able to obtain the soft carbon materials by carbonizing the polymer at 650, 950, and 1100 degrees. As you can see from the HRTEM images, the material three samples actually showed different levels of the graphitization, which means they have different level of carbon defects. We used various characterization technologies to identify the relationship between the carbonization temperature and the level of the graphitization. From XRD and the Raman technology, we understand that by increasing the carbonization temperature, the level of graphitization increases, which means the carbon defects decreases. We also use the XPS characterization to identify the types and the content of nitrogen doping inside the three different types of the samples. So we use a little bit of calculation to identify the level of graphitization, and we tested the surface area of the three samples, which actually doesn't show much difference among them. What is very much different among the three samples is the content of the nitrogen doping and the type of each nitrogen doping in the material. I will come back this later to explain how exactly nitrogen 6, nitrogen 5, and the nitrogen Q affect the battery performance. We started from testing the potassium ion batteries in the half cell configurations, and the results showed that nitrogen, the samples that is carbonized at 650 degrees showed the best performance, not only in a low current density, which is 50 milliamp per gram, all the way up to a very, very high current density, which is 20 amp per gram. So to put it into a perspective, when you charge and discharge a battery under a current density of 20 amp per gram, you are able to fully charge and discharge this battery in a time period of perhaps just a few tenths of seconds, 10 seconds or 20 seconds. So that really showcase the ability of this material to be able to be charged and discharged in a very, very fast speed. We also tested the material, the 650 degrees material at various current density and various cycles. The performance is quite impressive. At low current density, the capacity was very stable over 1,000 cycles, and at a high current density, the capacity is also stable over 4,000 cycles. By the time the paper was published, which is already 2 years ago, this performance actually benchmarked the performance of all carbon materials in the area of potassium ion batteries. We try to understand why the 650 degrees material can have such a good performance. What we did is we used different electrochemical techniques to characterize where the charge is stored in the material. Is it on the surface of the material, or is inside the bulk of the material? So the results showed that for the 650 degrees carbon material, it has the highest contribution of the surface potassium storage. And we also tested the potassium ion diffusion coefficient in the bulk structure of the material. And results showed that the 650 degrees material has the highest diffusion coefficient among the three samples. We also used the simulation as a further evidence to explain why we can obtain such a good potassium storage performance from the 650 degrees materials. What we did is we simulate the absorption energy between carbon structure with different types of defects, which is caused by the different types of nitrogen doping. And we compare the absorption energy between the different carbon structures and the potassium ions. What we found out is that for a single typed nitrogen doping material types, where we only have either nitrogen 5 or nitrogen 6, it shows a very high absorption energy. For dual typed carbon material, where both nitrogen 5 and nitrogen 6, the structure shows also very high absorption energy towards potassium ions. But for the single type nitrogen Q, the absorption energy is relatively low compared to the other two types of nitrogen doping. So it explains why the 650 degrees sample has the best performance, because this sample has the highest amount of both nitrogen 5 and nitrogen 6 dopants, and the lowest nitrogen Q dopant compared to the other two materials. Of course, we did a very preliminary demonstration using this material. We put it, we paired it up with the potassium Prussian blue, which is also developed by our group in 2017. So we use Prussian blue as the cathode material. We use the 650 degrees material as the anode material. We coupled them up. We made the full cell batteries, and we tested the batteries at two different types of configurations, anode limited and cathode limited configurations. And in both configurations, the batteries showed quite interesting capacity, which is consistent with either anode or cathode performance. And we calculate the energy density of these full cells, which is 130 volt-hour per kilogram. And this number is quite lower than the estimated number at the beginning of my talk. But considering it is a very preliminary work, and I believe this work actually gave us a very positive signal that by using carbon materials, we can achieve low cost potassium ion batteries. We can easily scale up the synthesis of the material. And with the research development between the time the paper is published and now, I have seen there is a large amount of work focusing on carbon materials for this topic. And the performance of carbon materials has been greatly enhanced since this work was done. The second example here I want to showcase is to move from carbon materials to the compound, which is sulfides here. We have done quite a few works on molysulfide, this material, both in sodium-ion batteries and potassium-ion batteries. From our previous work, we've learned that this material is very promising in terms of capacity. It is because the material undergoes two steps of storage of ions. At the discharge voltage that is higher than 0.5 volts, the material undergoes an intercalation processes where the ions are intercalated into the interlayer space between the molysulfide layers. At the discharge potential that is lower than 0.5 volts, which is the green area over here, the molysulfide is reduced to molymetal and potassium sulfide. This part contributes a very significant part of the capacity of the material. So for a lot of you in the audience, you may have known that molysulfide is a rising star, not only for batteries, but also for electronics, for catalysis. It is probably one of the hottest materials in various research domains at the moment. And the beauty of this material is that it has a very nice two-dimensional materials. where ions can be stored in between the layers. But the problem is ion can only insert or integrate into the interlayer space from the side of the layers. So what we think is if we can open up each layers, we can give extra tunnels where the ions can actually diffuse through the layer into the interlayer space. Then we can actually increase the intercalation sites. We can increase the surface area of the material. Both would contribute to the increase of the capacity of the material. So by using this so-called local molysulfide defects, we're able to take out some molysulfide molecules and make defects in each layer so that we can transform this 2D diffusion of ions into actually a 3D diffusion manner. So we use a very simple hydrothermal synthesis. I have just realized that a lot of the synthesis I have done over the years are actually quite easy, quite scalable. So what we did here is we changed the precursor amount of thiourea, which is the precursor of sulfur in this reaction. When we increase the amount of sulfur precursor, we can actually make cracks in the layers, which mimics the defects I explained in this slide. So use the HITEM, we are able to see there is cracks in each layer, so that if you look at it from side of the material, the layers are not continuous, it's discontinued by the cracks. We also synthesize the control sample where there is less defects in the material. So we can see from the side that each layer is a lot more continuous compared to the defect molysulfide. Not only do we able to create defects in the molysulfide, we also utilize this defect to increase the interlayer space, which can be verified by the XRD patterns, where the 002 peak shifts to the lower angle position, which means the interlayer space of molysulfide is increased from 0.62 nanometers to 0.91 nanometers. We use this material in both sodium and the potassium ion batteries, and we observed the enhancement of performance in both cases. In the case of potassium ion batteries, we observed a 40% increase of the capacity, and we also absorbed over 100% increase of the rate capability. And the increasement of sodium is not as significant as potassium, but it's also encouraging. We saw a 25% increase of the capacity in case of sodium, and also 39% of the increase of the rate performance in the case of sodium. So we, as usual, we try to understand what exactly these defects contribute to the increase of the performance. We calculated the diffusion coefficient of potassium ions, and we observed a 5 to 10 times enhancement of the potassium ion diffusion coefficient. We also characterized the surface charge process of the material, and the results told us that a lot more potassium is actually absorbed on the surface due to the defects instead of in the interlayer space. So as I explained in the beginning of this work, in a original 2D molysulfide where there's no defects in each layers, the diffusion of the ions are on the surface of each layer and in between the two layers. So it forms a 2D interlayer ion diffusion manner. But by introduce the defects of each layers, we open up the pathways for ions to stick into the material, and we open up the interlayer space where ions have more higher freedom to work around inside the interlayer space. So we essentially change the 2D interlayer ion diffusion into a 3D cross-layer ion diffusion. The last work today I would like to talk about is the long-range disorder, where we would like to use titanium dioxide, amorphous titanium dioxide, as an example, as titanium dioxide has been in the focus of research for perhaps 2 or 3 decades so far. We get to learn a lot about this material, most likely from catalytical performance of the material. Back to 2012, I discovered that titanium dioxide is a good material for sodium-ion batteries. I did this work in the University of Alberta in Canada, where this work was the first work of using titanium dioxide for sodium-ion batteries. It has been 8 years since that work was published, and I've seen hundreds work on the titanium dioxide, not only for sodium, but also for lithium and actually for potassium very recently. But they all focused on the crystallized titanium dioxide. So that got me thinking, can we use non-crystallized titanium dioxide, which is the amorphous titanium dioxide, to achieve the same or even better performance? Can we use the defects that are caused by the amorphization of the material to contribute to the capacity? I think the answer is yes. We started from the simulation work to verify that sodium intercalation is actually reversible in the amorphous structure of titanium dioxide. And we deliberately chose atomic layer deposition as our synthesis technology. And the reason is that we all know there's a lot of varieties inside a electrode materials, the size of the material, the thickness of the material, and there's also the conductive additive and the binder that are not active to store ions, but have to be added into the material in order to increase the electronic conductivity of battery. So the reason why we pick atomic layer deposition to synthesize titanium dioxide is based on the consideration that the technology can have a very precise control on not only the size of the material, the titanium dioxide, but also the thickness, which is 20 nanometers in our case. And we combined the ALD with the polystyrene colloidal crystal template, where we can obtain samples, we can obtain electrodes with exactly the same geometry, and the material will not need conductive additive or binder to work as electrode. So in this way, we're able to exclude the influence from other components in the electrode. Therefore, we can exclusively to study the effect of amorphization of the material. We use different post-annealing temperature to control the level of amorphization of titanium dioxide. That's also the beauty of this synthesis, which is very simple to follow, which can be done by anyone who has the ALD facility. So if we increase the anneal temperature to 350 degrees, we are able to obtain crystallized titanium dioxide. And by lowering the anneal temperature to 250 degrees, we obtain the material that has, a mediocre crystallinity of the material. But if we didn't anneal the material at all, then the as deposited titanium dioxide actually shows an amorphous structure. And we can also see from this characterization is that the geometry, the size, the thickness, everything else is identical in between among the 3 samples. We also use a combination of XRD, Raman, and XPS to verify if the materials are as what we think. By increasing the annealing temperature, we can increase the crystallinity. So by lowering the temperature, we maintain the amorphization of the material. We use the three materials all for the sodium-ion batteries. And the results are quite interesting, which is different from what we initially expected. So at a lower charge-discharge current, we see that the amorphous titanium dioxide delivered the highest capacity among the three samples. But the cyclability isn't as ideal as the crystalline material. But another interesting result we observed is this so-called self-improvement process, or in some cases, it's called self-activated processes. And we can, this process is characterized by the increase of the capacity over the cycles. And the lower the current density is, the smaller the cycles that are needed to finish the self-improving process. Interestingly, is that for our amorphous material, it needs a 0 cycle to reach the end of the self-improving cycles. At a high charge-discharge process, the cycles is much less than the cycles that are needed for the other two materials that have partially or completely crystalline structures. We also identified the storage sites of sodium ions in the three samples. What we found is that for disordered, which is amorphous material, and partially ordered carbon dioxide, titanium dioxide, the storage process is dominated by the surface of the material. And for the crystalline titanium dioxide, which is the long-range ordered material, both surface and bulk diffusion-driven charge storage process contribute to the capacity. So it tells us that by utilizing the defects that exist in the amorphous structure, we're able to shift the storage of the sodium ions from bulk to the surface. The advantage of that shift is that the surface storage process has much less resistance compared to the bulk storage process. It's easier to imagine that if you have ions moving around on the surface of the material, it will have wide open space to move around. But when you think the ions diffusing around inside the bulk material, then there's a very limited space and sites where the ions can be accommodated. Based on our observation of the surface and the bulk storage, we try to understand why this disordered material could have higher surface storage. We use simulation to estimate the absorption energy between the sodium ions and the 001 crystal plane of titanium dioxide. What we found is that for the amorphous titanium dioxide, the sodium absorption energy in the traditional electrolyte is much higher than the long-range ordered crystalline material. We also tested the charge transfer resistance, which reflects the resistance of the ions in the material, and we saw that the amorphous titanium dioxide has the lowest charge transfer resistance, which basically tells us the ions have the least difficulty while diffusing in the bulk of on the surface of the material. We also looked at the bulk structure how the bulk structure affects the ion storage. What we did is we tested the electronic transfer resistance of the 3 samples, and we found the amorphous material, amorphous titanium dioxide shows the lowest electronic transfer resistance, and the sodium diffusion coefficient also has the highest value in the bulk structure of titanium dioxide in the case of amorphous structure, compared to the partially and completely crystalline structure. I hope by introducing these 3 works, I'm able to convince you that sodium-ion and potassium-ion batteries are promising, will have a very, very bright future in terms of to provide a green and low-cost solution to store energy for various applications. And I also hope that I convinced you that disordered structures with various types of defects is a powerful strategy to regulate the structure of the electrode materials, so that we could push forward the performance of these 2 technologies. I haven't, I'm not showing any of the current work at the moment, but I can give you a little bit of flavor of what my students are working on at the moment. We actually found out that even with the same type of the defects in the same material, the effect for sodium and the potassium ions are different, which is very much out of our expectations. So we hope we can bring more new results in the future. We can present our new results to give you a better understanding in this strategy. I would like to wrap up with some acknowledgement to my students and my current collaborators at UCL Chemistry Department. I would also like to use this opportunity to thank all the wonderful people that I have been working with throughout my career. Some of them may contribute to the work I introduced today, and some of them may not. But I would really much like to pay my gratitude to this group of people. Without them, I wouldn't have gotten these results. And I would also like to thank the EPSRC and the UCL for the financial support of our work. And as my group just started last year, I would also like to shout out to everyone out there. You're welcome to apply to join our group, to apply for PhD student scholarships and postdoctoral scholarships with me. And thank you very much for your attention. I would like to answer your questions. Thank you.
Okay, great. So yeah, you did a wonderful job, and you show us new pictures, for all these kind of new technology, the emerging technology coming out. There are a few questions coming. Let me see. The first one. So Professor Xu, thanks for as a top scientist in new energy. Can you comment on the solar fuel cell battery supercapacitor, all this emerging technology?
I think every energy technology has their own pros and cons, and I often explain that to my students. For instance, when we're looking at the solar energy, it has unlimited resources. When we're looking at the fuel cells, it has a very, very low cost of the fuels. When we look at the supercapacitors, it definitely works better in terms of short time period power density compared to batteries. But I would like to take them as all the elephants in the room. They all have their strengths and they all have weakness. And for people working on different aspects, different technologies, I would encourage everyone just go for it. For myself, I would definitely go for batteries.
Okay, yeah, sure. Battery is a good choice. I think battery is, usable for a lot of kind of applications, and it can be solve big problems there. So, yeah, for all others, maybe that depends on different applications, right? Solar has its advantage for, like you say, is unlimited, right? Yeah, fuel cells, yeah, it's already there, but it need to get high efficiency. And yeah, that's a lot of room to, develop. I think you chose a good field. Okay. Yeah.
And
So we
one
move
more
to
thing
the,
I would like to add on that is that
please.
there are also current work in my group and in other groups that are looking at how to combine the different technology together. For instance, you can use a battery to charge the solar cells, and you can
Oh,
also use batteries to charge the devices that are presented by the previous two presenters. I think that would definitely open up a wide space for us to collaborate.
wow. That's interesting. Why use battery to charge for the solar cell?
Yeah, that's definitely a good idea.
Okay, cool. Yeah, we move to the next one. As you said, for the local MOS2 defect, how about the uniformity in the larger area? Can it be mass production?
So as I said in my talk, what the synthetic method we used is the hydrothermal. Uh, Depends on the volume of the hydrothermal, autoclave. I I believe it is a technology that you could it could be scaled up. Um, Depends on the level of mass production. I've seen the autoclaves for hydrothermal that are in the that has the volume of 10 liters. So I
Mhm.
haven't used that personally, but I definitely believe the reactions can be shipped from a small volume autoclave to a 10-liter volume autoclave. And
Oh,
as to the uniform of the surface area depends on the size of the nanostructures. Um, so our work, what we did is a small size of the nanostructures. I think the diameter of the sheets is in the range of 100 nanometers. So usually they're quite curvy because the size is small.
okay, that's let me recall. Months ago, yeah, several months ago, Professor Yuri Gogoltish has to talk about the vaccine. Yeah, they already have the mass production for vaccine. Yeah, that's good news for you. You can continue, for this direction. Yeah, cool. Okay, the last question is, yeah, this audience, yeah, should be want you to talk more about the 3D storage materials you mentioned. Yeah,
You mean the 3D the ion transfer in the monosulfide?
yeah. I think it's that part. Yeah,
Okay, so I may not explain well in my talk. So when we're looking at the 2D molysulfide, we naturally understand there's space between two neighboring layers, and ion can diffuse from the side of the sheets into the interlayer space. Because the what we did is we try to you can imagine that we try to open up holes on the each individual layers so that the interlayer space can be connected through the holes we made on the
uh-huh.
layer so that the ions at the lower level interlayer space can diffuse through the holes to the interlayer space on top of it or below of it so that the 2D diffusion model is changed
Mhm.
to a 3D diffusion model.
Okay. I see. Yeah, that's more clear. Okay, thank you very much, Yang, and you really great, person, great scientist. Yeah, I hope you done good job. Continue this way. Yeah. So as I can act, I deliver this virtual, certification to you for your wonderful talk, connect the world and and the universe. Yeah, you deserve.
Thank you very much.
Yeah. So you're welcome. Today we're almost finished. And next week, we're going to have the last week of iCAN X and 2020. So it's December 18, we will have the summit, iCAN X Talk Show. We name as 科学 X 大会. So the folks will be broke through as this year was we did on this stage. So I invited all the speakers in this 2020, iCAN X talks. There were totally about, 100 persons. We asked for videos. We asked the people to get into the panel discussions. We will discuss for the innovation of science and technology. We will discuss for the collaboration of science and technology globally. We will discuss for the future of science and technology, for the future technology, for the future scientists. So welcome to stay with us next week, Friday, 8 o'clock in the evening of Beijing. So welcome everyone to join this. See you next week. Bye-bye.